Okay, so this weekend we will be having the midterm finally, the first one. So this is the information you need to know about the midterm. It will be this Saturday at 1:30. It will be in this building. Some of you will be in this room, some of you in the other rooms still in this building. This U1, U2 are in the upper floor. Now the topics include for this midterm and for the next midterm will always be the topics we have covered, everything covered until the exam. So in the next midterm, it will not start from what we will do next week, but it will start from the first day of the semester until the second midterm also. You are supposed to know everything we have covered in the class. There will be a formula sheet. You don't need to memorize formulas. And in fact, in Piazza, I will probably start a discussion which formulas you want to be handed in, to be included in this formula sheet. If I don't include a formula in the formula sheet, it means I'm asking you to derive that formula. And, well, the vector signs, the units, they are important part of an answer. So to convince you that they are important, you will lose points for any vector sign that you don't put, or if you put a vector sign in a place that you shouldn't put a vector sign, you will lose points. You will lose 2 points for each. And in particular, well, there's an example over there. For example, if you solve a question of 10 points correctly, in the sense that you get a number which matches with the correct number, but you will lose 2 points if you have missed 5 vector signs in your solution and 1 unit in your solution, you will lose 12 points, so you will get minus 2 points from that question. So it will deduce points from the other questions. So remember to put the vector signs and the units in the correct place at the correct time. It is not just you put the units at the end. You have to, if you are making a numerical solution, you have to put the units in all intermediate steps. If there are vectors, you have to specify that they are vectors. If something that you use is the length of a vector, you first have to specify that it is the length of a vector. Now you can guess at least one question from the exam. You will be asked to draw free body diagrams. Either it will be a separate question or it will be part of the other questions. So that is at least one question in the exam. So you should learn to draw free body diagrams. Okay, any question about the exam? It will probably be around 4 or 5, not much. I mean, it will be 3 hours, not because it will take you 3 hours to solve the questions. It is just because you should have some relaxed time, so you should feel that you have sufficient time to solve all of them. Well, if you ask me, it will be easy. The easiest exam I will prepare. But the difficulty is most of the time when I try to prepare easy questions, I mean, we have been, during the semester, the students kind of get used to my way of asking questions which are kind of tough. So they expect some tough questions, and when I ask questions that I think are trivial, they just cannot solve it. It will be easy. It will be easy. Well, everything everything, including the things we do this week. You are responsible for your book, Giancoli. Plus, you are responsible for the things we have done in the class. A few of them were not included in Giancoli. Any other questions? Yes. 4 or 5? 4 or 5 questions. 4, 5, 3 hours. Sure. It will not be a multiple choice exam. You are supposed to show how you get your results in a proper way. And by that way, the etc. over there is, for example, if you, in your solutions, if you just make a circle over there, have some calculations over there, and just draw an arrow to another part on the paper, you will lose 2 points. Okay. I haven't yet prepared the exam, so I do not know. I mean, it will be Typically, it will be 5 questions with 3 sub-questions each. I mean, these 3 quizzes, from my point of view, all the quizzes you did until now were just 1 question with 3 sub-questions. The exam questions might be a bit harder than the quizzes. I hope you are not claiming that the quizzes were hard. Sorry? Any other questions? Bring your calculators. You might need them. Okay, in the beginning of the exam, how the exam will proceed. In the beginning, we will just distribute you the solutions. So you are required to read the questions first. Then I will just go to each one of these classes and explain you what each question is, one by one. If you want, I will also repeat it in Turkish, the explanation, and draw any diagrams related with the questions. Then if you still don't understand some words during the exam, you can ask the assistants. I will be going around also. Else? Okay then, let us start with this chapter, this section. Now, today we will be mainly discussing with the work, the concept of work, what we mean by work. Now we have typically an intuitive understanding of work. We talk about how much work we did, how an easy work something was, how hard work something else was. So what we mean by easy work, hard work is, well, if we apply a large force, for example, if you just carry such a small ball around, you will not say that you are doing a hard work. But if you were to carry 10 chairs around, you will say that you are doing a much more work. So the work you expect, it should be proportional to the force you apply. Furthermore, if you just carry this thing from here to just 1 centimeter, you don't claim to have done a huge amount of work. But if you carry this to the other end of the campus, you do think that you have done a huge amount of work. So the work should be proportional to the force. It should be proportional to the distance that you apply your force. Distance or time. I mean, if you carry this all around the campus, it will take you a long time also. But in physics, the definition of work is usually the force times the displacement we have. Now, this definition does have certain counterintuitive consequences. One thing is that if you take this book, your book, which is quite heavy, now this is not our book, but if you just hold it and carry it around with constant speed, constant velocity, you will get tired. But this definition tells me that I'm not doing any work whatsoever, because I'm applying a vertical force, whereas the displacement is horizontal. So there is no work done over there. Or if I hold this book, take the elevator, stand in the elevator, in that case, I am doing some work, because I'm applying an upward force. The elevator is taking the book upwards, so the force and the displacement of the book is in the same direction. So there is some work done over there. So that's kind of counterintuitive, but we will see why this definition is useful. Now, I don't know how many people had voted in the poll. The last time I checked, it was only 30 people about how we should carry this lecture. The difference is not that big. But nevertheless, I think we can do some applications, some demonstrations in the book and discuss the subjects over those demonstrations. Now, well, I need some volunteers. Different people if possible. You had volunteered. You did not. Hmm? Yes. Another one. Come on, one more volunteer. No? You are still sleeping? Now, this is our projectile. What we will do is, if you remember when we were discussing the conical pendulum, we had discussed that you could do this experiment at home, right? To measure the angle, just take a photograph. Well, that is what we will do. I will take a video of this projectile motion. Now, from that video, we will just show first, we had already derived that the projectile should go over a parabola. That is what we will determine. We will calculate its velocity, its acceleration. Once we know its acceleration, we will know its force, the force acting on my system. Once we know the force acting on the system, we can calculate once we know the force and the displacement, we can calculate the work being done on my projectile. So that is what we will do. I want 2 volunteers. Come here. One of you should hold this. This will be my meter stick, so I will know what the distances are in the video. No, don't throw it to your friend. Come here. It will be a short experiment. I want you come on, just throw it up. It shouldn't fall behind the other end of the table when I say go. Okay, not now. I will start the video. It shouldn't fall too far. It should, okay, hold on. Okay, you can remove the bag. It should go more or less to the middle of the screen and then fall toward the other end of the blackboard, more or less. Go. Action. Well, that was kind of too far up. Experiments are not easy. Hold on. Go. That was still too high. A bit lower. Yes, exactly. Now, not the middle of the screen, but to the lowest line over there. Go. Okay, that was nice. You will see what it was for. No, you can also sit down. So these are the videos we have. So can you see the video? Okay. Metin abi lambalar nereden kapanıyor? Tamam. Söndürelim. Okay, the video is dark, but okay, you will see the ball in a moment. There is your ball. Okay, so that was a nice shot. Let us find where it starts. Okay, this is the first frame. It is 202. Until 305. So this is the motion we will study. Now you will see what your ruler did. So let's just take the, it's almost invisible. Okay. This length is more or less half a meter. You were standing here, it was kind of over there. Now we need to track the position of the ball. So it is, we will treat it as a point mass. This is the position of the ball. So let's see how it can follow it. start it from the beginning. So these are the positions of my object at different times. The x position and the y position, there you see how x changes as a function of time. So you see that the x coordinate started at 0, the initial point was defined as 0. It goes until, no, it starts at 1 and it went until -2 more or less. And you see that it's a straight line, it's a motion with constant velocity, almost. And this is the y coordinate, how the y coordinate changes as a function of time. So you see it's almost a parabola. Now from this parabola we can also calculate the acceleration, the average acceleration, let's say. Now we should analyze the tools, analyze the data. So these are the graphs we have. Now we let us make a curve fit. I will fit the y coordinate. Well, it's a parabola. We don't expect a line. We expect a parabola. Now this parameter a is in fact, if you remember the expression for a accelerated motion as a function of time, it is just 1/2 acceleration t squared plus v0t plus x0. This is the y0. This is the change of y coordinate as a function of time. So this a value is in fact half the acceleration. Now it turns out that the acceleration is 11.2 more or less. It's a bit larger than the gravitational acceleration, but given the experiment we are doing, we are not that precise. So it is an expectable result. It's an acceptable result. Now for the linear line, for the y coordinate, x coordinate, so let me remove the y coordinate. So it is, well, this number over here, the smaller it is, the better the fit is. So it is almost a perfect line. So it is something like 1%, it deviates 1% from the perfect line. And we see that this is the x velocity. A is nothing but the velocity, the component of velocity in the x direction, which is minus 3.35 meters per second. No, it should be this one. Işıkları açamadık da. Bir açabilir misin? Siyah bastım, kırmızıya bastım. So now we have the data. Now, what can we say? The y coordinate, it should be 1 over 2 gt squared plus v0y t plus x0. This is how it should behave. And we had seen that it is given by, so A is 5, so minus 5.65 meters per second squared, t squared. You see where their units go? Plus B is 4.93 meters per second, t. And then C is 0.72. This is how the y coordinate of this object changes. Now, if you go to the x coordinate, along the x direction, it should be motion with constant velocity. So it should be v0x of t plus, no, this is y0, plus x0. And we find that it is given by minus 3.3536 meters per second t plus 0.97 meters. Now we can also try to do a parabola of it to find if there is some acceleration. Now the acceleration of the x motion is 3 times 10 to the power minus 2, so which we can neglect. Now there will be some acceleration because there is air resistance, but we see that the air resistance is almost negligible. It doesn't exist, more or less. Now let us just pick 2 points and calculate the forces. Now this is the, okay, how many of you know what a video is? Yes. Yes, it's just a collection of photographs, nothing else, a movie. You just see these movies very fast so that it creates the illusion that there is motion over there, but there's no motion. Now, the number of frames per second, the reason why you have seen that it is a slow motion was that the frames per second of this movie was 120. Whereas when it was moving, when I was playing the movie, it just showed 30 frames per second, more or less. Now, this tells me that if I take 2 successive frames, that is this raw number. Oh, you already have the time over there anyway. The time over there is nothing but raw number divided by 120, more or less. Now, let us just pick up 2 successive times. No, three or 4 successive times. Let us start with the raw. Let us pick something nice. Okay, this row. Now the time. Now the rest we can of course do with these fits. So we know its acceleration, we know the force acting on it on the average according to how the one we measured. So we know the force, we can calculate the work and all the rest. But we can also forget about these fits. Now let me just study how the motion behaves around this time, 0.25 seconds after the start of the motion. So 0.20 at t, x, y. At t equal to 0.25, the y coordinate is 1.62. T in terms of seconds, y in terms of meters, x in terms of meters. Now I had already said that whatever I write here has the units meter or whatever I write here has the unit seconds, so I don't need to write it down at each row. Now, y is 1.62. The x coordinate is 0.11. The next time, 0.263. X coordinate, y coordinate 1.63. Well, let me put one more digit. 618. 107. 0.079. The next time, 0.271. 1.648. 0.051. While I'm writing all these numbers down, instead of getting bored, you can think of the Kepler, what Kepler did. I mean, Kepler had all these thousands of numbers and without any computers. 0.280, 1.662, 0.024. Okay, this will be enough for me. Now, if you just enlarge the graph and plot these numbers, t, x, we know that x is just decreasing. It starts here. This is the first number. This is the second number. This is the third. This is the fourth number. If you consider the y as a function of time, the y is slowly increasing. This is the first number. This will be the second number, the third number, and the fourth number. Now we can talk about the average velocity as my object moves from this point to the other point. Well, I will need a calculator. This is why you should bring your calculator to the exam. Now, to calculate the average velocity between this time and this time, what I need to do is just the y velocity. Subtract this number from this number and divide by the difference of this number with this number. Now, if I just subtract these two, what I get is 0.015 divided by, if I subtract these two, I get 0.009. It is around 1.67 meters per second. 1.67 meters per second. The average velocity as my object moves from this point to this point in the y direction. Now in the x direction, I will do the same thing. It is just the difference of these two, which is 28. 0.028 and 0.009. It is 3.11 meters per second. So we are quite, well, your friend more or less threw at 45 degrees, somewhere around that number. But since we are considering a point very close to the top, it is natural that the y velocity is much smaller than the x velocity. Now let us calculate the average velocity as it goes from this point to the other point. So it is this difference. Let's just ignore the points for the time being. It is 15 divided by 8. 1.8788 meters per second. It is accelerating. apparently. Well, let's look at the x velocity. Now, by the way, the x velocity is minus. We are subtracting this number from this number. Now, if we subtract this number from this number, we get minus 28 divided by the time difference, 3.5 meters per second. Now let's continue. This time difference is again 15 divided by 8, 1.875 88 meters per second. And the x difference is 28 divided by 8, 3.5. And the last one, 14 divided by 9, 1.67. And the x speed is 27 divided by 9. Now, hold on. 3. Now what's going on? Now the y speed is almost constant, sometimes decreasing, sometimes increasing. The x speed, it is more or less constant. Now, so what's going on, really? What do you think is going on? Okay, theoretically it was simpler, yes? You had the time difference, we know the acceleration, so acceleration times the time difference should be the change in the velocity. So where is that change? Where? Time is increasing, the y direction is upwards, remember? So the y component of the velocity should be always decreasing. Well, the acceleration is downward, it is negative. Exactly. It's the error bars. Now, you see, the time difference between this point and this point is how much? 0.024. 26. This is the delta t. Delta t is this much seconds. The change in the velocity that we expect in such a time is 10 times delta t, 10 meters per second squared, 9.8 meters per second squared times delta t, which is around 0.2 meters per second squared. We should be seeing such a change. Well, that is quite below our precision. So that is something we failed, in a sense. Either we have to do a more precise experiment with more sophisticated data, or just taking 4 data points and analyzing is not enough for us. So let's do the other way around, the thing that we said we will not do. So we have already the y. I'm erasing this. Any questions in this one? Now we failed because our error bars is much larger than this change that we expect to measure. So just picking up 4 points and trying to estimate, calculate the acceleration will be useful for us. So y is a function of time. Minus 5.65 meters per second squared t squared plus 4.93 meters per second t plus 0.723 meters. This is our y coordinate. the x coordinate, this should be equal to minus 3.35 meters per second times t plus 0.97 meters. So these are our x coordinates and y coordinates. If I want to write the radius vector, the position vector at the time t, this is x of t, x hat, plus y of t, y hat, for any time t. Now we can calculate the velocity. The velocity at the time t is nothing but the time derivative of this thing. The x of t by dt in the x hat, the y of t by dt in the y hat direction. So I need to just take the derivatives of this y of t and x of t to find the x of t and y of t, the v of the speeds in the x and the y direction. So the speed in the x direction is a function of time t is minus (11.30 meters per second squared t plus 4.93 meters per second. This is the velocity in the x direction. The velocity in the y direction. Now this is the velocity in the y direction. The velocity in the x direction is the derivative of this one. Minus 3.35 meters per second. It's a constant. Well, this program is nice because I can also calculate the velocities here. So let us see. I want the x velocity. I want the y velocity. So these are the x velocities calculated by just taking the differences over here and dividing by the time, more or less. So you see that let me just enlarge it. So this column is the x velocity. So you see that it can be large, minus 3.9, but most of them are around minus 3.4. There are some 3.2, 3.3, towards the end especially. But it is the bulk part of the velocity, as we have calculated, is minus 3.35. Now the acceleration. X component of the acceleration. The x component of the velocity is almost a constant. This is 0. The y component of acceleration, it is just the time derivative of this one. It is minus 11.30 meters per second squared. This is our g. So let's see what this program gives us. Ax, Ay. Well, most of Ax is kind of small. Now the acceleration calculated in this experiment, you say it is just rapidly fluctuating. You get minus 3s, then the next moment it is 1, 7, minus 1, minus 8, 11. So that's kind of the fluctuation in our experiment. The measurements in experiments always fluctuate, independent of how accurate your instrument is. You will always get a distribution, not a single number. The hope is that that distribution is quite narrow, and most of your measurements should lie in around one number with some measurements. If you would just plot the histogram of this thing, that is the number of times that you measure a given value of acceleration, I would expect to see such a graph. Most of these measurements will be distributed around 0 or with some due to air resistance minus 0.01 meters per second squared. Of course, I will get some measurements that are very large in the negative, some measurements which are very large in the positive, but the bulk I would expect to be around this number. Now, if you look at the y component of acceleration, again you see some distribution over there. You get minus 41 meters per second squared in the y direction. But at the same time, you get minus 5 in the y direction. The average is somewhere around 13, 14. You see, most of the numbers are in that range. Oh, you also get some 10, 11s. And that is why probably we get such a large number. Now, the problem here is that the ball is small. Plus, it was quite dark. Now, when it was determining the position of the ball, sometimes this is not a point mass. We should have a point mass. When it was determining it automatically, it sometimes took this point as the position of the ball. Sometimes it took this point as the position of the ball. So although the ball didn't move much, if at some point it assumed that this was the position of the ball, if the successive moment it assumed that this is the position of the ball, so it will interpret the displacement of the ball to be quite large in that interval. So that is one source of error. The second one, well, I couldn't see this. So I couldn't really tell the computer what was 50 centimeters. I had chosen some length which was, Now that doesn't make any difference, it's the length. It's not positive or negative. But if instead of choosing this length as half a meter, if I told the computer that this was half a meter, then of course all the distances was enlarged. If the distances are enlarged, it's just assumed that the ball was moving much faster than it usually is. And so the acceleration was larger than it usually is. That would also explain this large number, minus 11.30. Since the meter that I told the computer what was the meter. Remember in the first lecture, we discussed that we have to discuss first what we mean by the units. So that is what I did. So I told the computer that my meter had this length. Well, let's see if I can show it again. Okay, so here is the meter. So this length from here to there. This I told the computer that it was half a meter. It was probably longer than half a meter. So the meter in this experiment, the meter we used, the unit we used is smaller than the real meter. So in that sense, we should have said that this is not the real meter, but it is the meter prime unit that the computer knows. This meter prime unit is probably smaller than the meter unit, the real meter unit. So that's why for the smallness of this meter prime, I get such a large number. But let us stick with this meter prime unit everywhere. Now, I know the accelerations. There is only acceleration in the y direction, and in the x direction, there is no acceleration. If I know the acceleration, I know the force acting on my mass. The force acting on my mass is just mass times the acceleration. The mass of my mass is, well, I measured at home before coming here. The mass is 0.028 kilograms. This is my mass, or 2.8 times 10 to the power minus 3 kilograms. This is my mass. So the force acting on my mass, 2.8 times 10 to the power minus 3 kilograms. Well, the acceleration is minus 11.30 meters per second squared in the y-hat direction. -2. You're right. So if you just multiply them, it is 31.64 10 to the power -2 newtons, 0.32 newtons, the force acting on my mass. This is the force acting on my mass. It's a constant force because the acceleration is constant all the time. So since the acceleration is constant all the time, the force is also constant all the time. If you give such an answer in your exam, you will lose 2 points. This is wrong. This is minus y hat. Well, in fact, if you do such a calculation in your exam, you would have lost 4 points. Now you save 2 of them. You still lose 2 more points. In the previous line, this is equal to minus this much in the y hat direction. Now you wouldn't lose any points. Sorry? So we have the force. Now let's calculate the work done on my object. Would you like to give a break? Okay. Yeah, you, yes. Others? Okay, so it's already break time. Okay, let's give a break.